And now I would like to invite Andrea Ruffino. So Andrea received a Bachelor of Science degree in Engineering Physics from Polytechnico di Torino, and then joined Master of Science degree in Micro and Nanotechnologies for Integrated Systems from Polytechnico di Torino, Grenoble Institute of Technology in France, and then Swiss Federal Institute of Technology in Lausanne, Switzerland. So he also holds a PhD degree in microsystems and microelectronics from EPFL in 2021. So since 2022, Dr. Ruffino is working with IBM Research Zurich, where he's working on cryogenic CMOS circuits for qubit readout and control. His main research interests include analog and RF integrated circuit design, wireless wireline transceivers, superconduction electronics, quantum computation, and quantum error correction. So, thank you.
So, hello everyone. Thank you for being here. And also thanks to the organizer for allowing me to present today. So today I will try to provide you with some circuit insights on cryogenic CMOS circuits for quantum computing. A little bit about myself. So as Elena said, I did my studies at EPFL, where I worked on cryogenic CMOS circuits for spin qubits for my PhD. And then now I'm with IBM Research, where I'm mostly focusing on cryogenic CMOS circuits for superconducting qubits. So these two are a bit the areas that I'll try to cover in my talk. Concerning my talk, this is the outline of my presentation. First of all, I will have a brief introduction about quantum and quantum computing. And I will try to set a motivation for cryogenic CMOS circuits in the first place. Then I will try to show some examples of circuits that you might have studied at university and draw their trajectory into research and then industrial research. And I will do that by providing examples of circuits that are used for spin qubits and circuits that are used for superconducting qubits. And finally, I will draw some remarks on the impact and importance of circuits in quantum. So, I guess most of you are familiar with classical computing. The unit of classical computing is the bit, which can be represented by a 0 or a 1, and this is represented in hardware as a low voltage level close to the ground for the 0, or a high voltage level in the case of a 1 close to the power supply. And then this type of information is processed in classical processors by transistors. And this is how classical computation is done. In quantum, the unit of information is the quantum bit, which is represented by a linear superposition with complex coefficients of the states 0 and 1. So this can be represented graphically by a vector in a three-dimensional sphere, which is called the Bloch sphere, where the vector can occupy any point on its surface. And how is this mapped into hardware? In order to do that, you need to have a quantum system where you can identify a subset of the two energy levels, a subset of two energy levels where you can identify a computational subspace so that you can map a 0 and a 1 state. This is done in superconducting qubits by having nonlinear LC resonators, and in spin qubits by trapping single electron in nanometric structures called quantum dots. Now, in order to address these systems, you need to send high-frequency signals whose energy matches the energy gap between the 0 and the 1 state. But this is only possible if the thermal energy is much lower than the energy you're using to address the qubit. So this means that basically spin and superconducting qubits require low temperature operation. So they are held at the base temperature at the sample stage of dilution refrigerators, which are large systems used to cool them down, while the electronics, which is classical electronics, which is needed for readout and control, is typically implemented nowadays by discrete cryogenic components, some of which are inside the dilution refrigerator, and room temperature instruments, which are outside the dilution refrigerator, and they are wired into the dilution refrigerator to connect to the qubits. As the number of qubits grows, this approach this wired approach doesn't seem to be scalable. So for this reason, cryogenic CMOS electronics has been proposed in order to, first of all, try to integrate the functionality which is required for qubit readout and control into single dies, and then operate it directly at cryogenic temperatures, so closer to the qubit plane, so to try to address or at least mitigate the wiring bottleneck that comes from outside with the heat load that these cables bring with them. What is the challenge, though? The challenge is when you want to operate your circuits at cryogenic temperatures, you have a limited power budget because this is limited by the cooling power the dilution refrigerator has at the temperature, at the stage at which your cryogenic CMOS circuits reside. And as you can see, this power scales down non-linearly, so it becomes increasingly more challenging to have low power circuits when inside the dilution refrigerator. But what kind of circuits are used for cryogenic CMOS circuits for quantum? The circuits that are required resemble, roughly speaking, transmitters and receivers which are used in radio transceivers. So they employ circuits which you might be familiar from RFIC design courses, such as low noise amplifiers, mixers, filters, and also mixed signal circuits, such as analog to digital converters, digital to analog converters, or oscillators, PLLs, and also there is quite a bit of need for digital circuits, such as memories and digital signal processors. So these are the building blocks, let's say the tools, that then are used to build cryogenic CMOS circuits for quantum, and I will try to show examples in the following slides of how these blocks are used in examples of circuits used for spin and superconducting qubits. The first set of examples relates to the work I did at EPFL concerning cryogenic CMOS circuits for spin qubits. And the first example is this quantum classical integrated circuit, which I designed in 40 nanometer technology, where there is basically a co-integrated matrix of silicon quantum dots on chip realized by minimum size transistors. And then there is a row column architecture which resembles a DRAM structure, which you might be familiar with access transistors to perform time multiplexing of the readout of the silicon quantum dots. And then there is a set of 3 radio frequency resonators, which are CLC resonators, which are used as impedance matching networks. So for example, here you see the combination of some circuits which are pertinent to the RFIC design world, such as the resonators, and circuits which are more in the digital domain, such as DRAM configuration. Another example of a circuit is the circulator. A circulator is a 3-terminal device that creates a non-reciprocal transmission depending on the direction of circulation. And a cryogenic CMOS circulator was designed in 40 nanometer technology, and in this circuit, again, I employed some RFIC building blocks, such as first and second order CLC all-pass filters. Then there were passive mixers, and then there was a part related to the LO path, including clock dividers and phase aligners, and then there was also a digital interface to perform tuning and control of this structure. And then the last example that I would like to briefly go through concerning spin qubits is the design of a cryogenic qubit receiver with a PLL. This is a circuit that was again taped out in 40 nanometer technology, including an RF IQ receiver with a PLL. So using, this circuit includes a low noise amplifier, which is built with an inductively degenerated common source LNA, And then there is a set of active IQ mixers, complex RC polyphase filters, so passive circuits, and then there is an LC tank-based VCO with an analog PLL and dividers. So as you can see, the flow for this circuit was the conception of a circuit, a schematic design, then a tape out, and then a measurement phase in cryogenic temperatures. So after these examples about spin qubits, in the next slides, I would like to show some examples of cryogenic CMOS circuits for superconducting qubits that are the result of a global effort from IBM Research and from the cryogenic CMOS team within IBM Research. And the first example is a cryogenic CMOS FinFET LNA, which was designed in 14 nanometer technology, which operates at 7 gigahertz, which is used for superconducting qubit readout. And again, in this case, this is a single stage inductively degenerated common source LNA with some techniques for source degeneration using transmission lines and output matching using transmission lines. And this was a very low power design that was then measured at cryogenic temperatures, achieving also 30 Kelvin noise temperature at 4 Kelvin. Then I think the most significant work that was designed in the group is this cryogenic qubit state controller, which is fundamentally speaking a large complex circuit, which is a cryogenic AWG. So this is a transmon qubit state controller designed in 14 nanometer technology that comprises a heavy digital part with a custom digital processors with waveform memory and instruction memory for waveform generation and storage and operation control, which then connects to 10-bit DACs with IQ mixers, baseband filters, and a transformer output matching to then generate the required modulated RF waveforms at the output. So this circuit was taped out in 14 nanometer technology, and as you can see here, it was packaged and then connected into the dilution refrigerator, as I was showing at the beginning, and it was operated at 3.5 Kelvin within the dilution refrigerator, and it was shown that this circuit can control superconducting qubits with the required accuracy, which is comparable to the room temperature electronics, which is the current solution. So what is the impact and the role of circuit design in quantum? In order to help quantum computing systems to scale to the required size, which is going to be needed in order to be able to solve useful problems, integrated circuits are going to play a role. And in particular, cryogenic integrated circuits are going to play an important role. ASICs, application-specific integrated circuits, are going to be needed at various levels, from room temperature electronics down to cryogenic temperature, and they are going to orchestrate with the full stack, which currently ranges from the software in the cloud controlling the whole system to the quantum hardware at the base temperature of the dilution refrigerator. And this classical hardware is going to perform very important functions in the quantum computing system, because it's going to be in charge of generating complex radio frequency waveforms, which are needed for the control of qubits. It's going to be employed to read out and detect the weak signals that come from the qubits. And then in the future, also it's going to be employed in order to execute the complex algorithms that are going to be needed when feedback is applied to execute quantum algorithms on large quantum processors. So circuit design is at the core of all these classical integrated circuit designs and is going to play a very important role. And then, as I showed previously, in this field, there are multiple integrated circuit design domains which are covered. Many of the most fundamental areas of circuit design are needed in cryogenic CMOS circuits for quantum, ranging from low-frequency analog circuits to RF, which is heavily present, mixed signal circuits, and also digital design. And all of these areas contribute to the overall system. And the typical circuits which I showed at the beginning, which I showed you examples of actuated in place in research, cover circuits across most circuit design domains. So to conclude, why is circuit design important in general and also according to me? I think circuit design is a very challenging activity. If all those who have done a tape out know how hard it is, how much work goes into it, but I think this is a very rewarding conceptual activity that allows to have and express a lot of creativity in inventing new circuits. Then, especially when you're part of a large organization, circuit design is a team activity, so it helps you develop collaboration and team skills. And then I think the most important part for me about why circuit design is so important and also fun is that you can move from conceiving, a functionality, a concept on paper with paper and pencil to implement it in real hardware that you can hold in your hands, and then you can go and measure in the lab, and you can see the real outcome of your work. And then these can go and contribute to progress in a research field, which could be quantum, and then later on, it could also produce some enhancements in society, for example, unlocking new possibility, which is what we hope for quantum computing. So finally, for me, circuit design is research. Design is certainly innovation, and it's also science. And I think this is why people should feel excited about contributing to circuit design. So with this, I'd like to conclude my talk. I would like to thank you for your attention, and I would like to take this opportunity to thank all the members of my past group at EPFL and Cryogenic CMOS team in Zurich and in Yorktown for being part of this effort and for making this possible. Thank you.
Okay, now we have time for questions. Yes.
How energy efficient are the quantum computers in comparison to the common household computer?
So right now, in quantum computers, at the moment, there are two big parts. There is the quantum hardware itself. In the case of superconducting qubits, basically this is highly energy efficient because the fundamental element of a qubit is a capacitor and a Josephson junction, which is a superconducting tunnel junction. But then on top of it, you need all the electronics to control and read out that. And the goal is to reach systems that have a scale in terms of number of qubits so that you can solve useful problems. And this is going to set a challenge on the electronics side so that you can meet the power budget which is allowed by the dilution refrigerator. So we're speaking about orders of magnitude for current systems as a target of 1 milliwatt per qubit. And then in the future, it should be even less because 1 milliwatt per qubit means if you have 1,000 qubits, you consume 1 watt, so you're already at the edge. So you should be able to scale this down. And this should ideally include the transmitter for control, the readout for, the receiver for readout, and also the clocking if in your system you plan to integrate that as well.
Okay, so I have two questions. The first one, how do you get device models at cryogenic temperatures? Do you get them from the fab, or do you do the characterization yourself? The first one. The second question is, my work is related to analog design automation using pre-computed lookup tables. So I wonder if the cryogenic design community explored using pre-computed lookup tables to capture the device behavior and use it for analog design automation as well.
Okay, thank you very much for the question. I think this hits very close to home, especially on the device side, because you know, I was involved, let's say, also in the early research developments of cryogenic CMOS circuits, and the way we designed the first circuits was basically by using room temperature models for the simulation, and then exploiting, you know, the circuit intuitions, which are at the basis of this whole event, to know as a circuit designer what will change in when designing your cryogenic CMOS circuits. For example, threshold voltage goes up, which means you have lower headroom, which means you need to go for topologies that do not require too much, a too stringent constraint on voltage headroom. Or, for example, flicker noise typically gets worse at cryogenic temperature, so you need to apply techniques to mitigate that. Mismatch gets worse. And now I think in the community, we are evolving on that front. So there are, especially for the organizations that can afford that, there are efforts in, you know, fabricating test sites with individual devices during the characterization and moving towards a more industrial set of cryogenic models. First, I would say developed in-house, from going from university research groups or industrial efforts. And I think eventually we'll get there where there will be, you know, PDK models provided by foundries directly. Then, can you remind me the second question? Because it was about using pre-computed lookup tables.
Yes, exactly, about using pre-computed lookup tables.
So I think that approach is very interesting. I'm not sure I would see a big difference in the usefulness of that approach, which I think is high, between room temperature design and cryogenic design. I think maybe this would come a bit more handy, considering that you might not have complete models. So you might come up with a design space exploration that puts you in a safer space with respect to certain problems that you might encounter at a cryogenic temperature. But let's say in the long term, I think that kind of technique and that kind of approach will be useful as much as it is for room temperature electronics.
Okay, thank you very much.
So I am not very knowledgeable when it comes to quantum computing or computers, but I do have a question. You mentioned the possibilities of quantum computing unlocking a lot of stuff for us. Can you give a few examples that are being developed or that you have ideas to develop to unlock?
Okay, so quantum computing, the idea is that there are certain problems which are not all the problems in the world, but some of them, there are certain problems that can be mapped into quantum computers more efficiently than they can be in classical computers. Examples of these are search algorithms, or for example, synthesis of certain molecules, or as Feynman proposed, also simulating quantum systems on quantum systems, because this is supposed to be more efficient than classical computing. So when the scale of quantum computers will reach the size which is needed to execute those algorithms, I think it will be possible to definitely show the advantage of quantum computers for those problems. At the moment, we are in a stage where we are peeking into it, but we're not there yet. So there is no definite proof at the moment with current hardware that this is possible, but the scale needs to grow a bit more.
Thank you.
Actually, I would like to ask a question.
Okay.
So, and I think, I mean, like, you know, maybe it's not necessarily was very, let's say, not kind. There is one very remarkable fact here. So the controller works also at a cryogenic temperature. It's not like a millikelvin range just for superconduction qubit, but it's also actually, it's a very, very low temperature. I think like 3 to 4 kelvins. I know that there are some attempts to design the controllers even for slightly lower temperature as well, but like it's pretty much, I think, defined by the stages of the core. So, but anyway, so the remarkable thing here is you cannot actually put any circuit you want at the 3.5, let's say, kelvins, because it's going to consume power. And hence, I mean, like, here is your trade-off, power dissipation, kind of, by circuit, and then complexity of the signal processing you can do in this controller. So can you just comment, I mean, like, so how you decide, okay, so I mean, like, what sort of controlling, let's say, function should be on chip at the cryogenic stage, and then should be actually taken away from the chip, let's say, at room temperature and so on?
Thank you for the question. So I think the early attempts were mostly about demonstrating that the fundamental functions which are required, which is control, readout, and clocking generation, are possible. But now we are definitely at the stage in which this is becoming more of a system optimization. So I think in the long run there will be, because of this trade-off between the power that you can consume in your chip and the complexity that the chip can have, there will be, fundamentally speaking, in the future, a distribution, I think, of electronics across different stages, where, for example, if your circuit doesn't need to be at 4 Kelvin, you could put it at higher temperature, and you could benefit from having more power available. But since we are in a circuit insights session, I think one important remark for circuit designers, because they're going to be the people building the circuits, is that I think we, in terms of optimal designs for low power, we have just scratched the surface. This is a rather emerging field, so there is no 20 years of development in this. So I think there is still a lot of margin for improvement in terms of power consumption, while keeping the performance, which is certainly needed, and the requirements are quite stringent. But I think there is still a lot of margin for lower power designs, and this is where good circuit designers will play a role and will make the performance better, and then it will become a system distribution problem, as I said before.
So maybe there are no more questions. And thanks, Andrea. Thank you for very interesting